Hey, welcome to the 23rd session of Flipped Classroom for Calculus. Today we're going to be talking about the mean value theorem and an introduction to differential equations. First of all, there's a theorem called Rolle's theorem, and it says that if you have a function f of x and it's continuous on closed interval ab, differentiable on open interval ab, and if f of a, the endpoints, equal f of b equals 0, then there's at least one value c such that f prime of c derivative equals 0. This would mean that there's a horizontal tangent at x equals z. X equals c because the slope of the tangent is the derivative. Here's a graphical interpretation of Rolle's theorem. Consider the function f of x equals x squared minus 1. Okay, notice that when x is negative 1 and 1, the function value is 0. So we've satisfied the first condition of Rolle's theorem. It's also a continuous function. It's also differentiable. Notice that there is one value here, could be more, c at x equals 0, such that the slope of that tangent line would be 0. Another theorem is called the mean value theorem. It says that if f of x is continuous on a closed interval ab, differentiable on our open interval ab, then there's at least one value c such that f prime of c equals f of b minus f of a, all of that over b minus a. Notice the right-hand side of this equation is what we call the average value of the function from a to b, or graphically it was the slope of a secant line. The left-hand side would be the instantaneous rate of change of a function at c. The next slide provides a graphical explanation of the MVT. Okay, here we have our function. It's outlined in red. Okay, notice that at the endpoints, okay, we have a, b, and what we're saying, the slope of this secant line, okay, which is f of b minus f of a over b minus a, there has to be some point, if the function is continuous, where the slope at some point c, the slope of the tangent, the derivative, is parallel to the slope of the secant line, meaning they have the same slopes. Therefore, they would be equal. Some things that come out of the MVT. Well, if f prime of x is 0 for all x values in the interval ab, then we're going to say that the function values at all those values are equal. Just think about it. If we have a slope that's horizontal, that means the function isn't changing. So therefore, the line has to be a horizontal line. Also, if f prime of x equals g prime of x, two different functions on closed interval ab for all values, then f of x and g of x are the same functions, except for the addition of a subtraction of a constant. For example, if f of x equals x squared, okay, picture that's a parabola, and g of x equals x squared minus 9, that's the same parabola, just shifted down 9 on the y-axis. Would these two functions on any interval have the same derivative, just shifted by the tangent lines would be shifted down by 9, or separated by a distance of 9. Okay? If you think of the average rate of change, average rate of change, f of b minus f of a over b minus a, and you think of f prime of c as the instantaneous rate of change, all we're saying there has to be some point where these two are equal in the interval. Okay? It also says there's one value f prime of c that would always be equal to the average rate of change. How to use this function? Alright, if you remember, for acceleration is the derivative of the velocity function, and velocity is the derivative of the position function. So let's say I tell you that a of t equals 9.8 meters per second squared. Since acceleration is the derivative of velocity, velocity must be equal to 9.8t plus some constant. Because if I take the derivative of 9.8t, do I not get 9.8, and the derivative of a constant is 0. Okay? So let's say that the same object starts from at rest. Maybe it's an object that's just dropped. Then we could say that the velocity at time 0 equals 0, and we can find c. Because what we do is we substitute 0 in for t into our velocity equation, and I get 9.8 times 0 plus c. It has to equal 0, therefore c equals 0, and our velocity equation in this case is v of t equals 9.8t. The derivative of position is velocity, so what function would have a derivative of 9.8t? Answer, 4.9 t squared plus any constant c. So our position function s of t equals 4.9 t squared plus c. If the initial distance at time 0 is equal to 0, then 4.9 times 0 squared plus c equals 0, and s of t just becomes 4.9 t squared. A differential equation relates an unknown function and one or more of its derivatives. The functions whose derivatives satisfy a differential equation is called the solution to the differential equation. Here's an example. Let's say I have a function y equals negative cosine x plus 3, and I tell you it's a solution to dy dx equals sine of x. What I'm saying is that the solution to dy dx equals sine of x is the function. How can I check this? If I take the derivative of y, do I not get sine of x? There are many solutions to this equation because it could be negative cosine of x plus 237 would also be equal to when you take the derivative of sine of x. Okay, so let's do a practice problem. I want you to find all possible functions with the given derivative y prime equals x squared. Well, you know that x has to be raised to the third power because when you take the derivative, you reduce the power by 1. So let's start with x cubed. Its derivative is 3x squared, but I need x squared. How do I get rid of 3x, the 3? I just divide by 3 to get rid of the coefficient. So now we're at x cubed over 3 plus c, because there could be a constant added to it because when you take that derivative, it's equal to 0. Okay, so we would say that the solution to this differential equation of x squared equals x cubed over 3 plus c. You can check that by taking the derivative. 22. Okay, here I'm going to tell you that acceleration equals 9.8, the velocity at time 0 equals negative 3, and the position at time 0 equals 0. Find the original position function. Step 1. What function has derivative 9.8? Well, we just did this, 9.8t plus c. Note that this is really a solution to the differential equation dv dt, which equals acceleration, okay, when equaling 9.8. To find c, use our initial velocity value. At time 0, velocity is negative 3. Okay, so negative 3 has to equal 9.8 times 0 plus c, therefore c equals negative 3. Okay, now v of t has to be equal to 9.8t minus 3. Step 3, find the function that has a derivative equal to v of t, and that would be s of t equals 4.9 t squared minus 3t plus c. You can check this by taking the derivative. When I take this derivative, I get 9.8t minus 3, and that in fact is our velocity function that we started out with. So the solution to the differential equation v of t, which is ds dt really, 9.8t minus 3, is s of t has to be equal to 4.9 t squared minus 3t plus c. Okay, how do we find c? I was told that the initial value at time 0 of s is 0, so plug that in. I get 4.9 times 0 squared minus 3 times 0 plus c. c must be 0, so the solution in this case is s of t equals 4.9 t squared minus 3t. This is really the solution to the differential equation ds dt, which is v of t, and it's 9.8t minus 3. Here's what I want you to do for practice. Page 261, 264, numbers 1 through 34. Extra credit. Have any of you figured out an easy way to find the original function if you're given its derivative? Okay? Note, please do not use the internet for this, as you will learn nothing. Try to think about it. First 2 people to email me will receive the extra credit. That's it, and have a good day.